Alright, so today we're going to be going over uniform circular motion. So this is essentially just uniform motion except around a circle. So some important conversions to know. So you got to know 1 radian is equal to 57.3 degrees around a circle, and that 2 pi radians is going to be equal to a full circle, which is 360 degrees. And then the equation for angular velocity is going to be delta theta over delta t, which just gives us how much degrees elapses between the velocity around a circle. And this is kind of just a depiction, which the variable for angular velocity is going to be w, in which, if you remember, velocity is, the variable for velocity, but velocity around a circle would just give us tangential velocity, which is not velocity that curves around a circle, but that's depicted by w, which is what we're going to use for angular velocity. Alright, so let's take a look at number 23. So this figure shows the angular velocity versus time graph for a particle moving in a circle. How many revolutions does the object make during the first 4 seconds? So if you remember, on a velocity versus time graph, the area under the graph is going to give us the displacement of the position, which is going to what we're trying to find out here. So first, let's find out the area under the graph. So let's break this up into a few shapes: a triangle, a square, and then 2 rectangles. So first, let's find the area of the 2 rectangles. So for the rectangles, we're going to have a base of 2 and then a height of 10. So 2 times 10 is 20 radians, and we multiply that by 2 because we have 2 rectangles, which is going to be 40 radians. And then let's find out the area of the square, which is going to be a width of 1 and then a height of 10, which is going to give us 10 radians. And then the area of the triangle is going to be a width of 1 and then a height of 10 divided by 2, which is going to be 5 radians. Now, if you add that all together, you're going to get 55 radians, which is going to be the displacement over the 4 seconds. Now, we want to turn 55 radians into a unit of revolutions. Now, 1 radian, we know that 1 radian is equal to 57.3 degrees. All we need to do is multiply 55 by 57.3. And we are going to get 3,151.5 degrees, which is going to be our displacement over 4 seconds. Now we want to find out revolutions. So if you remember, 360 degrees is 1 whole revolution around a circle. So all we need to do is divide by 360 degrees, and we get that revolutions is going to be, the revolutions around a circle in 4 seconds is going to be 8.75, or we could also round that to 8.8 revolutions, since 360 degrees has 2 significant figures. But 8.8 revolutions is going to be our final answer. Alright, so let's take a look at number 24. So this figure shows the angular position versus time graph for a particle moving in a circle. What is the particle's angular velocity at t equals 1 second, t equals 4 seconds, and t equals 7 seconds? So here we're going to use the angular versus angular velocity equation, which is going to be delta theta over delta t. And then we're going to convert the radians into degrees to give us the angular velocity. So first, we're going to leave in radians when we do the calculation and then convert it at the end. So first we want to find the slope. Since this is a position versus time graph, we want to find the slope that's going to give us our velocity. So a t equals 1 second is going to be around here. Our slope, if we use the angular velocity equation, it's going to be delta theta, which is going to be negative 2 pi minus 2 pi, which would be 2 pi right here, minus 2 pi, and then over delta t, which is 2 minus 0. And you would get an answer of 2 pi, negative 2 pi. And so we're going to write our answer as negative 2 pi here for now. So that's going to be our angular velocity. This is going to be in radians first, and then we'll convert it. So now let's find the angular velocity at t equals 4 seconds. So we can see that the position versus time graph has kind of flatlined at t equals 4 seconds. So again, we could assume that the angular velocity is zero, because the position is not changing. So we're going to have as our angular velocity, 0 radians for t equals 4 seconds. And now let's look at t equals 7 seconds. So we can see the graph is increasing right here. And now we want to use the angular velocity equation. So we're going to have 4 pi minus 0. So 4 pi minus 0 over delta t, which is going to be 8 minus 6. And that's going to give us an answer of 2 pi, which is, it's 4 pi over 2, which is 2 pi. So our angular velocity is going to be 2 pi radians. Now we want to convert this into degrees. So 1 radian is equal to 57.3. So all we need to do is just multiply all these answers by 57.3. And we're going to get our final answers for angular velocity. So at t equals 1, our angular velocity is going to be negative 360, in which it's going to move counterclockwise 360 degrees every second. And then t equals 4 seconds is going to be 0, and t equals 7 seconds is going to be positive 360 degrees, in which it moves clockwise 360 degrees every second. And these three are going to be your final answers. All right, so let's take a look at number 25. So this figure shows an angular velocity versus time graph for a particle moving in a circle. Starting from theta equals 0 at t equals 0, draw an angular position versus time graph and include appropriate scale on both axes. So feel free to pause the video and try this out. All right, so let's take a look at this question here. So we're given a velocity versus time graph here. Again, the area under the graph of velocity versus time graph is going to give us our position or displacement rather. So let's find out the area of the interval from 0 to 2 on the velocity versus time graph. And this is all going to be in radians per second as well. Radians and then seconds. So we're not going to convert anything. So the area of this first rectangle is going to be 20, which is our going to be height, and then times 2, which is going to be our width. So it's going to be 40. We had a displacement of 40 radians in the first 2 seconds. And then we want to find out the area from 2 seconds to 4 seconds. That's going to give us our displacement from 2 to 4 seconds. So you can see it's the same rectangle, 20, and then a width of 2. So we're going to have a displacement of 40 radians. So 40 plus 40 is going to be 80. So at 4 seconds, we're going to have a position of 80 radians. And then we see the velocity versus time graph kind of is 0. So that means that we're not moving from 4 to 6 seconds. So we could plot another point at 80 radians. And then at t equals 8 seconds, from the interval of 6 to 8 seconds, we're having a velocity or angular velocity of negative 10 radians. So again, we can find the area of this box right here. That would give us our displacement, which is going to be a width of 2 and then a height of negative 10. So we have a displacement of negative 20 radians, in which we're going down at t equals 8 seconds. So our line's going to go down something like that. If we connect everything, it would look a bit like that. The line over here should be straighter. It should be a linear line. But that is going to be our position versus time graph for this question. All right, so let's take a look at number 27. So the Earth radius is about 4,000 miles. Kampala, the capital of Uganda, and Singapore are both nearly on the equator. The distance between them is 5,000 miles. The flight from Kampala to Singapore takes 9 hours. What is the plane's angular velocity and with respect to the Earth's surface? Give your answer in degrees per hour. So feel free to pause the video and try this out. All right, so let's take a look at this question. So we know that the Earth's radius is 4,000 miles, and the distance between both countries is going to be 5,000 miles, or the locations rather. So first, let's draw a little depiction or visualization. So our radius is 4,000 miles. Since we're dealing with angular velocity here, we want to be looking at circumference, which is the area on the outside, or rather the perimeter on the outside. So if you remember to find circumference out of radius, you would just do 2 pi r. And since we know radius is 4,000, we just plug in 4,000 for r, in which we get a circumference of 25,132, or rather 33 if we round it up. And that's going to be our circumference. So 25,133 meters. And the distance between them is 5,000 miles. Or this is actually miles, not meters. But so let's say the capital of Uganda is right here, and then Singapore is right here. This distance is 5,000 miles. And the distance of everything is 300 or 25,133 miles. So let's use some proportions here to figure out how much angular distance they're covering in that 9 hours. So we know that there are 5,000 miles between the locations. There's 25,133 miles over uh, a whole circumference of the Earth. We also know the circumference of a circle is 360 degrees, or a circle is 360 degrees rather. We want to find out what degrees is going to give us the proportion that's going to be equal here. Now, if you do some rounding here, we would have 5,000 over 25,000, which is also equal to 0.2. So, which is 1/5. And 1/5 of 360 degrees is going to give us an x value of 72 degrees. So between the capital of Uganda and Singapore, we are going to be traveling 72 degrees around the Earth. So 72 degrees, which could look something like this. It would be a 72-degree like pizza slice. So our angular velocity, or rather our angular displacement, is going to be 72 degrees over the 9 hours. Per 9 hours. We want to find out the answer in degrees per hour. So all we need to do is do 72 divided by 9 hours, and we're 72 divided by 9 is going to be 8. So our displacement, or angular velocity rather, is going to be 8 degrees per hour. And that is going to be our final answer.